So welcome our next speaker, Michal Lipinski from Dioscuri Center in PBA. Will speak about tracking dynamical features.
Okay, so thank you for the introduction. So yes, so today I'll be talking about our recent paper that is written together with Mrozek and Tom Day and Ryan Slechta. And the goal of this paper and also the goal of the talk today is to develop some tool or some algorithm that will allow us to study and analyze the future of a chosen isolated invariant set when the dynamics that we have behind this dynamical system also evolves. And we will be doing this in the setting of combinatorial dynamics, in particular in the context of multivector fields, which are a generalization of Forman combinatorial vector. Okay, so before we get to this combinatorial world, let's start with this cartoonish example to see what we actually want to do. So suppose that we have this continuous vector field, and we are in particular interested in this isolated invariant set S. Here it is just a sample, and we want to be able to follow it when the dynamics itself changes. Yeah, and we want to follow it and see as it morphs and it drifts through a space. So if it would be a periodic orbit, it would also change shape and so on. And the set that we follow might also go at some point through some kind of bifurcation-like events. So, for example, here the saddle merged with another saddle, and they created this monkey saddle. So we would like to say that at this point, this monkey saddle is a natural successor of the saddle that we started with, because it absorbed it, and it also inherited the dynamical features of the saddle that we started with. So from now on, we will want to follow this new isolated invariant set, and we will be tracking how the new set evolves. So that will be the goal. And for the first part of the journey of this saddle, we will use the notion of continuation. Here's let's say, simplified definition of what continuation is in classical dynamical systems. But let me explain it. What does it mean with the picture? So let's again start with our S. Let's build isolating neighborhood around it, and let dynamical system to evolve. And when we are getting to the point that we are just about to lose the isolation, we build another isolating neighborhood to keep the isolation, and we let the dynamics to evolve again. And we play this game with the dynamical system, and if we are able to construct such a sequence of isolated neighborhoods that guide one isolated invariant set to the other, then we say that those two isolated invariant sets are related by continuation, what can be interpreted as saying that those two sets are basically the same isolated invariant sets, but in different time steps. And we also know that both of them share the same dynamical properties. But at these bifurcation-like events, we cannot continue anymore. That's the idea of continuation. So those bifurcations provoked us to combine this idea of continuation together with the persistence homology, and we'll get to this later. So we'll use this persistence to get over those bifurcations, and after that we can still display. We can still again play this game of continuation. We can follow our new idea. So this will be our goal. To have this algorithm that will produce some kind of a summary of the evolution by the invariant set as the dynamic change. Okay, so let's get to combinatorial multivector fields. So let me start with very informal few slides about what multivectors are. First few slides are for those who know what Forman vector field is. So just to give you the idea in which this generalization went. So multivector fields are defined for any finite topological spaces, which can be represented by posets, and we have this favorite family of posets that are generated by Simplicial complexes. So you generate this poset by just taking all simplices, and you can consider phasor relation. So here is original definition of Forman vector field. We have this partition, we have this sparing function, and we have three conditions which defines this Forman vector field. Let me restate it with other language. So basically, you can think of Forman vector field as a partition of your space into singletons and doubletons, such that doubletons has form consists of two simplices, such that one of the simplex is a phase of codimension one of the other one. And the dynamics, and you can retrieve the dynamics that this combinatorial vector field generates just by reversing arrows inside the vectors, and you end up with this directed graph. And basically, paths in this directed graph reflects the dynamics that you have by considering this Forman vector. And the difference with multivector fields is that instead of making partition into singletons and doubletons, you are allowed here to make any partition of your space into subsets that we call multivectors. The only constraint is that all those sets must be convex in terms of a poset, which means that if 2 points are in the set, then everything in between is also. And to get the dynamics induced by this partition, you again have this default downward direction in the poset, and you just make a directed clip inside of every multivector. So again, we have this directed graph that represents the dynamics here, and you can put this into this formula. Okay, so but for those who don't care of Forman vector fields, I have, I think, an intuitive way of how you could think about multivectors. So let's simplify our setting and suppose that we have the cellular complex, and then we can define multivector field just as a partition of the complex into subsets called multivectors of specific form. Namely, all of those blocks have at most a closure of the boundary that is missed. This closed part of the boundary is set that we call mouth. And what is the dynamics generated by this partition? So you can imagine you have this block, and there is missing part of the boundary, so there's no wall, and this missing part of the boundary is exactly the area through which everything pulls out of the block. So this is the missing part of the boundary, corresponds to the outward flow, and symmetrically solid part reflects corresponds to inward flow. You can think of them as a dynamical black box. We don't know what is going on inside. However, those subsets looks kind of similar to Wajewski sets, so we can distinguish some of them using this Wajewski principle. We can distinguish some of them as a special subsets, which by Wajewski principle, if multivector considered as a Wajewski set, let me repeat. Because Wajewski set is a compact set such that the exit part is closed. And Wajewski principle tells you that if you compute a relative homology of the set relative to the exit part, and the resulting homology is non-trivial, then you know that there is something invariant, necessarily something invariant inside. So we can use this idea to distinguish special multivectors that we will call critical, because from this point of view, they represent something that keeps something invariant inside. So using those two rules of this transition and distinguishing those critical multivectors, we can build this combinatorial model of dynamics. So this model has two layers. We have combinatorial. So we have this directed graph that represents the dynamics, and we have partition and context that represents the topology. Okay, and as on the previous slides, the paths and the solutions of the dynamical system, the trajectories are simply the infinite paths in the corresponding directed graph. We actually distinguish some special kind of those trajectories, but maybe this is, we call them essential. They grasp the actual dynamics, but maybe there's no point of getting deeply into that. But the idea, but using those essential solutions, we can define invariant sets. The definition is the same as in classical settings. So we say that the set is invariant, and for every point inside, we can find this essential solution that stays inside for in plus and in negative type. And we also have the notion of isolation. However, it is weaker than the classical isolation in two ways. First, it's we don't require to this isolated set be in the interior of the isolated neighborhood. And the second weird thing is that in those settings, isolating neighborhood may actually isolate two different invariant sets at the same time. But the most important properties of isolation are still preserved here. And the most important for us concept is the Conley index. So we have the Conley index theory adapted to combinatorial settings, and Conley index is the invariant of topological invariant of isolated invariant set. Describes the nature of the set, and it is defined as a relative homology of so-called index pair consisting of two closed sets. So we define an index pair for isolated invariant set as those two sets. such that E is a subset of P, and those two sets must satisfy those three kind of standard conditions. First condition tells you that if you are in P, you cannot escape P without going through E. E is our exit set. Second condition tells you that if you are already in the exit set, you cannot retreat and come back. And the third one tells you that the thing for which you construct this pair must be an invariant part of the difference of these sets. And we proved that this Conley index is well defined. You can choose any two index pairs for S. You will always end up with the same model. Okay. This is example of Conley index. Here should be this attractor should have one generator in 0 mode. Okay, so in order to talk about this continuation, we need a notion of small perturbation. But since we are in this 3D world, there is nothing like an epsilon perturbation. So we need to find some kind of a counterpart. And you can play with some examples to notice that if you try to model this changing dynamical system and you want to build a multivector field model of it, you will notice that when you change a little bit original system, then the smallest thing that will happen to your multivector field might be one of two cases. So you can encounter merging of two multivectors into a single one, or you can have this splitting of one multivector into two smaller ones. So those two operations are our combinatorial perturbations. And and we call them atomic rearrangements. So again, we have two smallest things that might happen to our multivector field. So we have this we call it atomic refinement when one of the multivectors splits, or we have atomic coarsening when two multivectors start to form one multivector bigger. And you can actually play with this idea, and you can start to analyze the topology of all multivector fields. But I don't have time to talk about this. This was just a nice picture. But since we have already this notion of perturbation, we can define the continuation, but in combinatorial settings. So the idea of this definition is exactly the same as the one that we have seen at the beginning. There are two main differences. So first of all, we cannot have the family of dynamical systems parameterized by continuous time. So instead of that, we have a sequence of multivector fields that such that the next one is always an atomic rearrangement of the previous one. So this is our counterpart of evolving dynamical system. And the second thing is that instead of guiding set with isolated neighborhoods, we guide those systems with those sets with index pairs, because they are because isolation is quite weak in combinatorial world, but the index pairs are just enough. But the idea will be this. Okay, and we'll need this definition to achieve the goal I was talking at the very beginning. So let me remind what we are looking for. So we assume that we have this sequence of multivector field such that the next one is an atomic rearrangement of the previous one. So this is our morphing or evolving dynamical system. and we choose isolated invariant set that we are interested in. So we want to know the evolution, the future of this particular one set. And how do we analyze this? How do we find this future? So we split it into the smallest, those small steps. So we are asking, what's the natural successor of my isolated invariant set, but in the next step? So in order to do that, we construct the minimal index pair for S0 in V1, in V0, such that this index pair is still a proper index pair in V1. So if we are able to find this index pair will uniquely give us S1. And after that, we can restart the procedure. So we are asking what's the natural successor of S1 when our system changes. So we find the minimal index pair for S1 in V1 in such a way this is also a proper index pair after this perturbation. And this gives us the next step. And we repeat this procedure as long as possible. But the question is, of course, how to actually find those index pairs and those successors. So we considered all possible cases, what can happen to your multivector field, and we gathered what should you do with something that we called tracking protocol. So, for example, the first point is the simplest case when one of the multivectors splits. Then you have this very easy formula for finding a successor. But if we have this merging of multivectors, we have this coarsening, then things become more complicated, and we have to consider different cases. These are different situations, but they still give you a direct receipt on how to find the success. And of course, you may fail. Continuation may fail at some point. You might not find success at some point. So we, of course, prove that this makes sense. And the consequence of also of these theorems is that the protocol is in some sense complete, meaning that if you cannot find a successor by following protocol, then there is no successor at all. So yeah, and I didn't mention, but it is not trivial, I think, but it may happen also in continuous world that you may continue in two different ways. But we argue with this theorem that the choices that the protocol makes are optimal. We generate the canonical candidates for a successor. And this canonicity is expressed by those inclusion. It tells you that the successor that we find is the most similar to the set that we had at the previous step. Okay, so how this would look like on the picture. So suppose that we have this sequence of multivector fields. Here we don't care where they come from, but in general, there are multiple trials there are multiple propositions of building those multivector fields. There is some early attempt. Right now, Mrozek and his students are going for building multivectors from cloud of vectors and also from differential equations in rigorous way. And me and Pavel also we prepare the algorithm to build multivectors from discrete trajectories. So you can build them in different ways, but for now we don't care about it. We have this sequence of multivector fields. And let's say that we are interested again in this multivector that represents actually a saddle, and we want to see how it evolves. So going with this protocol, applying this protocol, when some multivectors merge or split, the protocol will return us, will give us this sequence of those orangish sets, which represents this process of a drifting and morphing isolated invariant set. Here are, I denoted which case is applied from the protocol, and yeah, we have also we are following this this set S. T is just another saddle that lives somewhere else, and this is a case 3 that tells us that if something is changing outside of our set of interest, it does not disrupt the properties of the set that we are following. So yeah, so with this protocol we get this sequence of isolated invariant sets that reflects this change in time of it. Okay, so again, we started with the sequence of multivector fields, and by applying protocol, we get this sequence of isolated invariant sets in different time steps. And also as a byproduct, we get this sequence of index pairs, of those connecting index pairs that first of all allowed us to find it. And we want to make use of them because index pairs encode dynamical nature of the set, because by index pair you define the Conley, our discrete. So we want to also include this sequence of index pairs into our final description. And as I mentioned at the beginning, we'll use this also to overcome this bifurcation problem. So we will try to build a filtration, a zigzag filtration of those index pairs to turn into persistent language. And in the paper, we proved that if you have, okay, because what is important here, that if you are able to follow, then what is important for us now is that for example, those two index pairs are actually both of them are index pairs for this single isolated invariant set. And this is also true, for example, here. So those two index pairs are index pairs for S2 and so on and so on. So by making this observation, we can actually construct this. We can connect two consecutive index pairs using this theorem, which says that if we have any two index pairs of the same isolated invariant set, then you can construct a sequence of inclusions, index pairs connected by inclusions in such a way that all of those inclusions induces an isomorphism. And the full receipt how to connect them is quite ugly, but in most cases, this is universal receipt how to connect index pairs, but in most cases it's not. You don't need all of those steps. So we know how to connect all of those index pairs that we get into how to connect them and gather them into form of zigzag filtration. And it's a consequence of what I said, moment ago, that if we actually compute the persistence of that filtration, we will get something extremely boring, because all those inclusions that we have here induces an isomorphism. So if we started with one generator, our initial Conley index had just a single generator, then we end up with just a single full bar. And if our initial Conley index had k generators, we end up with k full bars. But that's okay. That's what we wanted, because continuation is supposed to preserve dynamical features. So this actually proves that the continuation that we define kind of makes sense. But as I mentioned, this persistence language will help us with those bifurcations. So we can go further, and there is actually additional step in the protocol that exactly tells us what should we do when our isolated invariant set goes through some kind of bifurcation. We can no longer continue, but we still with those instructions in the protocol, we can find the set that kind of, in some sense, absorbed the set that we were followed. Okay, and okay, does the observation that at the level of our multivector field, it may look like we are going through a bifurcation when something that represents one subtle and something that represents another subtle merge into a bigger structure that has Conley index of a monkey subtle. But this is just the level of the resolution that we were given. But at the bottom, it might happen that there is no real bifurcation. This is just a comment that I wanted to say. Okay, so we know how to go from S6 to S7. So we know what is our natural successor that we should follow. But there is a question how to connect those two sets, how to connect the Conley indices of those two sets, because the strategy that we had before does no longer apply. So in order to do that, we introduced a special version of index pairs that have this nice property that if you intersect them, you still get an index pair. But this intersection is no, it is not an arbitrary kind of intersection in the sense that I should order my slides indifferently. It's not arbitrary intersection, because what we will get using but the construction that we have here kind of translates the generator that we started with to the generator of the new structure that we will get. So using this idea of intersecting index pairs, we can fill this gap in the filtration that we try to build in such a way that Conley index generators will be translated from one set to the other. And again, full receive is quite ugly, but again, it is the universal receive, and in most cases, it will be simplified. Okay, and after we get over those bifurcation-like events, we can again continue continuing in the way that we had at the beginning. Okay, so to summarize, what we can get from this protocol is the following description of the evolution. So again, we started with the sequence of evolving system represented by the sequence of multivector fields that such that the next one is always an atomic rearrangement of the previous one, and we have chosen a set of interest that we want to follow, and the protocol gives us at the end the sequence of sets that represents how it moves through the space, and we also get this barcode that you can interpret as a timeline of the Conley index of the set that we are tracking. So it, in particular, it records the moments when we go through some kind of bifurcations. So yeah, so you can see that for the most of the time we get a single generator in the Conley index. After this merging with other set, new dynamical property feature appeared, so it is encoded in the barcode that we get, and this is what we get in the end. So we have those two elements that we get as a result of the protocol. Okay, and I think there is still, I consider the thing that we did here as a kind of intermediate step. We are getting more comfortable with tracking Conley index with persistence in combinatorial settings, but there is still a lot to do in that direction, and my ultimate goal that I would like to at some point achieve is the picture like this. I think it is this weird kind of barcode that actually encodes the evolution of the entire Morse composition. So, and it should encode how all generators of Conley indices jumps between Morse. But this is for the future. And I will stop here. Thank you very much.
Thank you, Michal. Questions to Michal?
Can you say more about this weird picture on the last slide?
I have, for now, I have only a fuzzy idea how to get there, but I have some intuition. But what is on this picture is every column here represents a time step, and every column actually is a Morse graph, Morse Conley graph. So it's actually positive. It's kind of a barcode that is spanned on a sequence of posits. And I would like to record how generators of Conley indices jump between Morse sets when your Morse composition changes.
So we have another question. When you were tracking these things with a zigzag, would the heap graph somehow annotated with homology be more appropriate? So you were tracking these isolating sets with a zigzag, I guess.
Yeah,
here. would it be more appropriate to keep track of a heap graph of the individual components and then annotate it with the homology? I guess that can't be used. Well, so the heap graph would be with respect to the projection of the time.
But wait, but the read graph of what?
So if I restrict my function to your isolating neighborhood, and I take the function that is just a projection onto the time axis. We can talk about that.
But yeah, I can see exactly what you mean, but yeah, I don't see it, but
I mean, it's a little bit like what Gunnar was talking about, right? That he was tracking his evading paths, and he was defining a zigzag on pi naught. So that's
okay.
what I'm saying. But it's okay. We can talk later.
Yeah, I can see like how where do you see those read graph? Because we need those index pairs, right? Because they encode the Conley index.
So you would annotate the graph with the index pairs. So you would track. So for each branch in the graph, or for each edge in the graph, you would annotate it with what is the Conley. And then it contains, I mean, similar kind of information, but in a different way.
Okay, you can next slide.
Thank you for the nice talk. Wonderful illustrations. All your illustrations have been in 2D. So do you, would it be a big change to extend to higher dimensions?
And theory is set up for actually multivector field theory. It was part of my PhD thesis. Is for any finite topological spaces. So all of that also can be defined. It works in any finite topological space. So it doesn't matter about the dimension you are doing. I mean, of course, there's the problem of actually computing this, but
Yeah.
but theory works.
Okay, thank you.
Other questions?
I have a clarification question. So is my understanding is that continuation is like prevented where you like kind of merge two saddles, right? But are there other reasons why you could not continue?
Other reasons other than bifurcation.
I guess.
In continuous case, I think always just bifurcation prevents you from finding the successor in the thing after the perturbation. And in combinatorial world, I mean, there's no in combinatorial world, there's not well-defined. We don't have well-defined notion of bifurcation. But I would say that what is my intuition of what is a perturbation in combinatorial? I would also say that only such events prevent us from continuing.
Okay.
I don't see any more questions. So thank you, Michal. And it was the last talk before lunch, yes? So thank you, Michal, thank you all, and let's go for lunch and meet in the afternoon.
Maybe the point was good enough, but I guess in theory it's different, right? So if you have your fields, you have all these isolating layers of right, which you can go forward.